Hello, this is vector operations part 2. So the next operation we are going to define. So let me just go back for just a second here, okay? Just a second, and refresh your mind that we had previously defined an operation between addition of two column vectors. And so for the sake of these sketches here, what they look like, if they have equal length and we apply the definition adding up entry-wise or component-wise, coordinate by coordinate, entry by entry, we obtain a new vector, okay, which is still a column vector of the same length. Now, this operation, even though we went to all this specification level of specification, this operation really is nothing new because, well, maybe what is new is the shape. Now we're talking about column vectors, but if you remember, so maybe I draw you here a little cloud of memory. We used to have a row operation that was something that looked like this, say alpha r sub I plus r sub j. And what's going on here with this notation is that we have scalar multiplication by one row and then addition. And so when we are working with matrices, we know that one row versus another row, they have the same number of elements, right? And so this business of adding them together, adding, you multiply by a scalar and then add them together, but you're always working in a particular location, and you're doing that for all locations, all possible locations, right? So basically this operation of addition is in the same spirit, in the same sense of one of the row operations that we have when that we apply when computing the reduced row echelon form. And so the next operation is even more intuitive because remember how we were saying in RREF calculations that we can say something like alpha r sub k, where r denotes a row. Well, now, so this scalar multiplying a row, this becomes a new row. So basically what you do here is that you distribute that multiplication on every possible element, every possible entry of that row, and therefore you obtain a new row. Well, here the spirit is the same. However, now we're multiplying a scalar that looks like a dot like that by a column, and by doing that we're gonna carry out this multiplication with every possible entry of that column, and then we're gonna end up with a column vector of the same length. So suppose we have a vector in Cm, we have a scalar alpha, which is a complex number. Then what we write here as alpha u, this is going to be the new vector, and this alpha u is also a member of Cm. It's going to have the same number of entries. And the entries of this new vector, alpha u, these entries here, this is entry I, okay, or the index for the location. The entries of that new vector alpha u are defined at a scalar level as the multiplication of alpha times the ith entry of the vector, right? So alpha is a complex number, and so is u sub I. So this is a multiplication of two complex numbers, which is well understood and well defined. And this is the definition of scalar multiplication. So here's an illustration of this type of operation. So suppose we have a scalar here with a value of 6, and we have a vector. This vector is a member of C5. In other words, that is u sub 1, here is u sub 1, u sub 2, u sub 3, u sub 4, and u sub 5. And then when we write alpha u, this is a new vector. Okay, this is completely a new vector. This is something that looks like scalar times column vector. So that would be the scalar 6. And what's going to happen here is just exactly in the same spirit as when we were doing RREF calculations. This scalar multiplication is going to carry out throughout every possible entry of this vector. And so that gives us 6 times 3 in the first location, 6 times 1, 6 times minus 2, 6 times 4, and 6 times negative 1. And that's how we obtain that's how we obtain the entries, the values stored on locations 1 through 5 of the new vector, which we call alpha u. So we have specified the definition of equality among vectors, among column vectors. We have defined addition of column vectors and scalar multiplication. So one scalar multiplying a column vector. Turns out that with those definitions, then this set CM of vectors, column vectors with M entries, has certain properties. The first of which is called additive closure for column vectors. The word closure here has to do with the fact that this is the idea that we have an incoming u vector, another incoming v vector. Excuse me here for just a second. So an incoming u vector, another incoming v vector, they are of the same length, okay? And this gives you a new vector, which is called u plus v. Well, it turns out that each of them, this is a member of CM, that means it has M entries. This is also a member of CM, and then the new vector, the addition of the two, is also a member of CM. So that idea of the length, the number of entries, the length of the vector is being preserved under this operation. This operation respects that if you take a member of CM and add it together to another member of CM, the new newly obtained vector is still a member in CM, and therefore you say this set CM, this set of column vectors, is closed under addition when addition is defined in this way. So that's the idea of closure for column vectors, which we have already defined. And so this is a number here. This is a list of such properties. So the next property has to do with scalar multiplications, called scalar closure for column vectors. Same type of idea. You have a scalar, you multiply that by a column vector, and then that gives you a new vector, which is still a column vector of the same length as the original. So this new vector is a member of CM, and the previous vector was also a member of CM. So there is a closure for this operation in this set of column vectors CM. Then the next property is called commutativity. There is commutation under addition of vectors, okay? Under this operation, using the addition operation in the sense we have defined, then there is commutativity, which means that you can add the vectors in any order you like and you still get the same vector, okay? So if you add u plus v, you obtain a vector. If you add v plus u, you obtain a vector, and then you compare those two and they are the same thing, okay? So there is commutativity with addition of vectors. The next property has to do with associativity. Associativity means that you're still considering the operation, one of the two operations we define, which has to do with addition, right? So we are adding vectors. We're in that business of adding vectors. This is not about flipping or changing the order in which things are added. So you still have u plus v plus w, u plus v plus w. If you're reading this from left to right, there u, v, and w appear in the same order, in the same locations. So this is not unlike commutativity, where you're here's u and here's w, and then you send u second, right, and then v first. That was commutativity. Here, the only thing that is happening is that you make little groups, okay? So you group together and you choose to carry out the operation in certain order. So you group these two and then first compute v plus w. This will be a first new vector, and now once you have that new vector, then add that new vector to v. And if you group v plus w and do this calculation in the order I just described, you will obtain a vector. And now choose to do the group in a different fashion. Do u plus v first, okay? And that gives you a new vector, and add that new vector to w. And if you compare the latter with the former, then you find they're exactly the same thing. The next property tells us that under vector addition, there will be an element of CM, which is such that when that vector is added, when that element is added to any arbitrary member of CM, under the definition of vector addition, you obtain exactly the same thing. In other words, that by adding that element, by having that element being one of the two incoming vectors into the addition, the output of that addition, the new vector, remains exactly the same. And that means it remains unchanged. And so that is the formal definition of a zero vector. This is something that we know from sets of scalars, such as the complex numbers and the real numbers and so on. But this is simply inheriting that property from complex numbers throughout all entries, okay? Also, addition is an operation under which there exists one thing called inverse under addition, in such a way that once we have defined this specific member that's called the zero vector, which has this property, we will see that under addition there always exists a member of CM such that you can add that member to this newcomer, and then you would obtain the so-called zero vector, right? So this is the formal definition of having an inverse under addition. Then we have some type of associativity with scalar multiplication. If you look in both sides of this equality here, we don't change the order. Alpha and beta appear, alpha appears listed first. The only thing that's changing, this is again in the same spirit as how we were writing those parentheses there. So this means that you first choose to compute the scalar multiplication beta times u. That gives you a vector that I'm calling the new vector. And then you do second alpha times that new vector. That will give you a vector. If you choose to first multiply alpha and beta, then obtain a scalar and multiply that new scalar times the vector, you will compare the latter with the former and will find that they match. They are exactly the same because of this property. There is also distributivity. If you have a scalar, which is an outsider outside of this operation addition, you could think of this exactly as we did with real numbers or complex numbers. So you could distribute that scalar multiplication across the addition of these vectors, and then so you would, another way of thinking of this is the parenthesis is around u plus v, so you could choose to do u plus v first, and that gives you a new vector, and now carry out the scalar multiplication with that new vector. If you compare that to do the scalar multiplication alpha u, do the scalar multiplication alpha v, and then add up those two vectors, you will find that they match. The latter matches the former. Okay, and so there is also a sense, this looks similar to the previous one, but now notice that what's in the addition here, what's being added are the two scalars. So when you have the addition of two scalars, this is still scalar multiplication, and when you have the addition of these two scalars multiplying a vector, you could choose to add those two first and then do the scalar multiplication, or you could do each of these scalar multiplications first, add them together, and you'll find that this is exactly the same. And there's a last property, that's the so-called one for the operation scalar multiplication.